Products and Noetherianity.
Thanks. So first of all, this is joint work with my postdoc, William Simmons, and I should point out that William is my source on all matters algebraic, and so the plan was to finish the slides in time to ask him to check them for me, and that didn't happen. So all mistakes in them are definitely my fault, and also when, not if, I make a mistake about the algebra, please by all means point that out. And also, of course, with especially some of the stuff from logic showing up, by all means stop me and ask questions. So I should say what I want to talk about. So William and I are working on a paper which will be finished in the proverbial 2 months that all unfinished papers will be finished in. And really the point of this talk is sort of to be a kind of prologue to that paper, in that the paper is going to be a mix of a bunch of sort of calculations in differential algebra, really motivated by some ideas that are coming from proof theory. And so what I wanted to do here was give a somewhat more informal sort of introduction to the proof theoretic side of that, and where we're coming from and why some of the weird stuff in the paper, where that came from and why it's going to look the way it did. So the starting point is an idea that I think is familiar to certainly everyone in the room, the idea that there are mathematical theorems where you have computable bounds. And so most of my examples, of course, will come from algebra and differential algebra. So this first one is the theorem that says membership in an ideal is testable, and in an algebraic ideal is testable. And one way to say that is to point out that if you have finitely many polynomials generating an ideal, and you know their degrees, and you know the degree of the polynomial whose membership you want to test, then you don't need to check all conceivable linear combinations. There's a bound for the degrees of the coefficients when you look to express G as a linear combination of the generators of S. Implicitly here, the generators of S are Fi, which I seem to have forgotten to say. And similarly, which one is this? Oh, primality of an ideal given by finitely many generators is testable. And this theorem looks very similar. If you know in advance the degrees of the polynomials that generate an ideal, and you want to know if this ideal is prime, well, you only need to test primality up to some bounded degree. And from my perspective, what's important here is that you have these inputs, which in both of these are some bound n on the number of variables and some bound d on the degrees of the polynomials. And there's an output, a bound r, that tells you how far do you have to go, how high do you have to look, how big could the witnesses be. And many proofs in mathematics, when they prove that things have computable bounds, they prove this in the obvious way by writing down computable bounds and showing that they work. And those theorems certainly have well-known computable bounds. But there are other methods that don't explicitly give computable bounds. So there are methods that indirectly prove that computable bounds exist, or essentially equivalently prove that some algorithm terminates in a finite amount of time, but the proof, at least in the proof, you don't see explicit bounds. They don't tell you how long that running time is. And these statements are in a little bit of tension with these ideas from proof theory. So actually, there are foundational results from proof theory that say that really oughtn't happen. That actually, if you have a proof that bounds exist, you ought to know what the bounds are. That in some sense, there are no non-constructive proofs that computable bounds exist. And there's some tension between these because these are, this is a theorem from proof theory that I'll state more precisely, slightly more precisely in a moment. On the other hand, the first, these are not literal quotes from papers, but one certainly reads things like this, and people mean something substantive by that. So I want to talk about what's going on there. So I need to be a little bit of logical formality
so
here.
You can't argue by contradiction.
So you can argue by contradiction, but implicitly there must be another proof that doesn't. Let's see. Yeah, no, that's fair. So any proof that looks like it's a proof by contradiction of a statement that should have computable bounds, actually there must be some more direct proof.
But when you say things are computable or you have a computable bound, do you mean that in the sense of computability? That there is an algorithm to compute a bound, whereas you can't really find a bound yet?
So, let's see. There are these subtle issues about computability and computable versus non-computable fields that I want to sort of not talk about. But putting that aside, I actually mean that if you have the sort of statement that ought to have computable bounds in the computability theory sense, then you actually really should have explicit bounds in the, here is a function, explicitly given exponentials, maybe iterated Ackermannian. I mean, they may be very poor bounds, but you should have an explicit function that tells you how big the bounds are. This is not an obvious statement by any means. This is sort of the theorem that created the field of proof theory. And so let me try to state this a little more precisely. So the key idea here is there are statements that ought to have bounds. And I'm going to call these pi to n for mostly technical reasons. So pi 2 here, the pi is supposed to be a for all. So logicians like to think of for all quantifiers as being like products. And the 2 tells you there are 2 blocks of quantifiers. So pi 2 is really a fancy way of saying it's a for all exists statement. So formally what I want to do is talk about statements of this form. They have a bunch of inputs, which I'm here calling n1 through nk, and for the moment think of them as integers, though that will get a little complicated. I'm going to talk about quantifying over a class of structures. I'm calling it k, but you should, for all examples in this talk, k is either, say, algebraically closed fields or differentially closed fields, or maybe polynomial extensions of one of these. So for all possible values n, and for each structure, there are some witnesses, there are some bounds, b1 through bd. And what should happen is some first-order statement that depends on these values should be true in the structure.
Where are the b's?
The b's are also, for the moment,
Okay.
integers.
Oh, integers.
Yeah, or natural numbers, I should say. They'll typically be positive.
And,
Oh, m's are also integers then.
and,
Yeah.
and you are okay with the b's depending on the structure?
And for the moment, I'm okay with the b's depending on the structure, though it's certainly, so I'm going to make a distinction in a second between uniform bounds and non-uniform bounds. So yeah, for the moment, it's very intentionally written that you could say different structures could have different bounds. And really the example I'm thinking of here is that if k is all polynomial extensions of an algebraically closed field, but k includes extensions with n variables for every n, then you would expect the bounds for many theorems to be non-uniform. They'll depend on how many variables you have. So that's the sense in which you might expect non-uniformity. So for the logicians in the audience, I'm doing something that logicians don't normally like to do, which is I'm mixing what we usually think of as the first-order language of a theory. So here, the languages here would be the language of rings and the language of differential rings. So the things you can talk about in a ring using addition, 0, 1, multiplication, and maybe the derivatives. But I'm mixing that with numeric quantifiers from the integers. Yeah.
But you're not really mixing them in that your quantifiers in the natural numbers are far on the outside, and inside B, there is nothing to do with natural
Yeah.
numbers, and you're also not bounding the complexity of phi in any way.
Right. Yeah, so that's exactly what matters here, that phi can actually be any first-order sentence in the usual sense of logic with all the quantifiers you want over elements of the structure. So if we're talking about a ring, you can quantify over all elements of the ring, or if you're talking about a field, all elements of the field. But you shouldn't have quantifiers over the natural numbers in here. That's what's important, that phi is just an ordinary statement, but on the outside we have these quantifiers over natural numbers.
And do you make any assumptions or requirements about how phi with subscripts depends on its subscripts?
computably. In all practical cases, very, very, very simply. But yeah, the real answer should be computably. So you should be able to, so the operation that tells you how to take your natural number parameters and turn it into first order formula, that had better not be too weird. Okay. So formality aside, actually, this is just a formal way of saying, exactly the sort of trying to say, what are these statements with computable bounds? What do they look like? So that first example I gave, right? D and N are those inputs, they're the N's. And then R is that exists statement. This has uniform bounds once you've fixed N. So in fact, that B, that bound R, doesn't depend on the particular structure, though in other examples it might.
So you mean it doesn't even depend on the FIs?
On what?
It doesn't depend on the degrees of the FIs?
FIs are also bounded by total degree.
Yes. Yeah, this is the bad notation. The FIs are the elements of S,
Okay.
which I should have said.
Okay.
Yeah.
Okay, so that wasn't in the original statement?
No, this is a
was.
copy of the original statement.
No, it is not.
I think it is.
I think it is.
The FIs were there, and
All right.
the FIs, I should have said the FIs are the elements of S. I
Right.
just switched.
Okay.
I was
All right. Okay.
compiling two
All right,
versions.
fine.
I forgot to keep my notation consistent. And so the point here is everything after the if K is an algebraically closed field, all the rest of that is actually a first order statement in the language of rings. So in particular, Alice disagrees.
The number of polynomials in S.
I'm cheating because that's a that the
Finite
degree.
dimensional
It's a finite dimensional extension of known
Right,
degrees.
so take it all.
So you don't, in this
Okay.
case, it's actually a property of rings. You don't need to worry about the size of S. Maybe,
Right.
if I'm really writing as a first order statement, I should probably say, you need to say the size of S initially. But putting that in detail aside, in particular, what's important here is that you can't, in first order logic, quantify over all polynomials of arbitrary degree very easily. But once you've fixed the degree, you can quantify over polynomials because there's a finite number of coefficients you have to specify, and you just say, well, for every possible choice of coefficients, and that's finitely many first order quantifiers. So once we've fixed Dn and R, you can write down a particular first order formula that expresses this. That's the important point here. And without specifying Dn and R, you can't do that. And of course, this is quite computable as a first order formula. It's very sort of easy to take those parameters and write this down as a statement.
May I just ask something
Yeah.
a little bit based on the result, let's say?
Yeah.
So suppose you have this formula that depends on Dn and R. Is there a way to minimize D fixing N and R?
To minimize D. What do you mean by
In
minimize?
other words, find a set of generators for S
Oh,
of the lowest degree where this statement is still true.
there must be some such D, but I don't know that there's.
Right.
I don't know that there's an easy way
It's
to.
bound to be low by zero.
Well, so computably, there's only so many polynomials of degree less than D, so you can do some. So computably, you can presumably do that by just searching for
Searching,
lower
right.
degree polynomials.
But can you obtain that D from your formula? From the first order formula?
Certainly not in an immediate way. Yeah, no, the formula is not doing any heavy lifting. It's really just writing down the obvious stuff, and it's not going to have any sort of substantive work hidden in it. So the idea here is these pi2n formulas are the sort of things for which you would expect to have computable bounds. In the sense that, first of all, if you've proven one, it's certainly reasonable to ask about computable bounds, right? You could certainly ask, well, is there a function that tells you these b's, or at least tells you a maximum possible value for these b's as a function of the inputs, the n's, and maybe depending on k. And conversely, in some sense, the statement that a function is computable is actually of this form. So in some sense, any proof that something is computable is actually fundamentally a statement of this form, or proving that something is equivalent to a statement of this form.
In general, what are the conditions that you place on that K?
What are the conditions? So
Sufficient conditions.
sufficient conditions. So computably axiomatizable collection of structures is certainly good enough. You can probably get away with, you can certainly get away with less than that, because Banach spaces work there, for example. There's some, sort of exactly what K can be is actually a little open, but certainly computably axiomatizable structures suffice. Classes of structures that are axiomatizable by things like not just first order formulas, but countable unions of first order formulas. So again, like those, like all possible polynomial extensions, like those also work. So it goes somewhere beyond first order collections.
So, I guess to what extent, it seems like what you are saying in some sense is that every function is computable, right? So, or somehow that I can't code a non-computable function in a nice enough class of structures.
It's more like you can't code a non-computable function in a nice enough class of structures. So the issue is that for anything like a reasonable class of structures, this is going to be testable. So this is going to end up being, sort of the stupid computer program that just tries values of B until, if you know this is true, then the stupid program that just tries values of B till one of them works is going to work. So you know that the function must be computable, and then you start asking, well, how fast is it given that it's computable?
Okay.
So first of all, I sort of was taking this as implicit, but I should say it precisely. So what do we mean by saying a statement has computable bounds? We mean that there's an actual computable function, say for each k, which computes bounds on this. And then if we would say it has uniform bounds if the function doesn't depend on the particular choice of structure. So this is sort of implicit in what I was saying earlier, but it's good to write it down correctly. And
So when you say decidable structure, computable structure, you mean decidable structure, not recursively presented structure? Because you want the thing on the right to be, you want the satisfaction relation to be recursive.
that's,
Yeah.
you can do better than that, but if you want it, but yes, it's certainly safe to assume that for this talk.
Okay.
The general results are in fact more general.
Okay.
So the point is, in fact, under reasonable assumptions that include sort of the cases I want to talk about, provable pi2n statements have computable bounds. So if you can prove it, there must be computable bounds. And if your class of structures is closed under ultraproducts, then they must be uniform. So this is, in some sense, the main reason ultraproducts show up in these areas, that precisely what they're good at is turning bounds into uniform bounds. And less obviously, I claim that these are constructive theorems. So there are theorems that say, under the right assumptions, if you can prove a pi2 statement that it has computable bounds, if you can prove it in a class closed under ultraproducts, those bounds are uniform. And I claim that that proof is constructive, so if you can prove these statements, you should actually be able to produce explicit bounds, right? That's the substantive claim here. And let me say this is a theorem, well, quasi-theorem, since I haven't said what reasonable is. So if we have a proof that a pi2n statement holds in a nice enough class of structures, then actually somehow we should be able to look at this proof and turn it into explicit bounds. some sort of explicit calculation. I just want to quickly point out before I get into say more about that exactly what you expect is that when you write down statements that aren't pi to n, they tend not to have explicit bounds. And that's very much a tendency. There are certainly interesting exceptions. But for example, the RIT problem, which I know some people in this room have thought about a bunch, if you write it down in this format, it's a pi 3n statement. So it has the form, for all stuff, there exists a bound such that for all natural numbers, something happens. And the RIT problem is essentially equivalent to asking whether there's a bound on that exists quantifier in the middle. And precisely because you then have these additional for alls afterwards, it's not the sort of thing that automatically has bounds, and sort of typically statements like that don't. But sadly, saying they don't typically isn't quite the same as saying that any particular one doesn't. In fact, I mean, if one looks through the literature, so most sort of open questions in the literature of the form, does such and such a statement have explicit bounds, are exactly of this syntactic form. And this sort of recurring question that people ask. All right. So the proof theory, so in the 30s, right, Gensen sort of founded the field of proof theory with these results. And what Gensen did is, Gensen said that if you take a non-constructive proof of a pi 2 statement and you formalize it in Peano arithmetic, so you give not a journal proof, but a formal proof in Peano arithmetic, then you could take this proof and do a bunch of really combinatorics, just structurally rearrange the proof until you had a constructive proof. Gensen's proof is not useful for this sort of thing in practice, mostly. There are a couple examples in the literature. So the problem is Gensen's technique is called cut elimination, and the process of transforming a proof into its constructive form, it is an explicit combinatorial process. It is just a very, very slow combinatorial process. It has sort of astronomically large bounds. I'll say how large in a moment. But in the 50s, Gödel developed this technique called the functional interpretation or the dialectica interpretation. And the functional interpretation is actually a linear time version of this. So you can take again, a proof in formal logic, a sequence of formal deductions, and in linear time, step-by-step transform it into a constructive proof. There's a cost, which is you have to change your system of logic. So you can no longer work in what we usually call first-order logic. You need to work in what's called a logic of higher types. So what this means is that in addition to talking about the natural numbers, you're going to end up with functions, computable functions from the natural numbers to the natural numbers, and functions that take functions from the natural numbers to the natural numbers and give you a natural number or give you a function. You get sort of lots of higher type objects. So that's sort of the price you pay for this linear time transformation. There's another important feature of Gödel's version, which is that it has a property called compositionality. And what this says is what the transformation is local. The way you change one part of a proof doesn't depend on what happens elsewhere in the proof. Cut elimination is highly non-local, by contrast. So the reason that's important is actual proofs, the way people write them in journal articles, are not written as formal deductions in Peano arithmetic. So it's not obvious that just because you can combinatorially rearrange proofs in Peano arithmetic, that you can combinatorially rearrange actual human readable proofs. And the act of translating a journal proof to a formal proof in Peano arithmetic is extremely time consuming in itself. It's probably at most maybe quadratic time, but it's poor constants. It's very slow in practice. So the nice thing about this compositionality property is it says you don't have to translate the whole proof. What you can do is isolate the important parts and just translate little bits. And that you can do in a reasonable amount of time. All right. So, especially since I know some people have worked very hard on getting good bounds on some statements out of differential algebra, I should point out that these results do not give good bounds. So, we have this notion called the fast-growing hierarchy. So here's the fast-growing hierarchy. The first function is just the successor function. f0 of n is n plus 1. And this sequence of functions is indexed by transfinite ordinals. So the successor operation just says repeat the previous function n times. So for example, f1 of n says add 1 to n times. So f1 of n is 2 times n. f2 of n says multiply by 2 n times. So it's 2 to the n times n. f3 ends up being essentially a Tower exponential bound. If you go through this hierarchy, and then I should say at limit ordinals, you diagonalize over the sequence. So f omega of n is fn of n. So f omega, the first infinite step, is essentially the unary Ackermann function. It has basically Ackermannian bounds. F omega plus 1 is going to be an iterated Ackermannian rate of growth. So the proof theoretic bounds come out of this hierarchy. So what Gensen showed is that P&O arithmetic has something that we now call a proof theoretic ordinal. The proof theoretic ordinal of P&O arithmetic is epsilon 0, which is omega to the omega to the omega to the omega iterated. This is where the ordinal epsilon 0 comes from. This is sort of why it's significant. And if you have a proof in P&O arithmetic, then the bounds are going to be bounded by f alpha for some alpha less than the proof theoretic ordinal of the theory. So if your proof was in P&O arithmetic, you're going to be, the bounds are at worst f of omega to the omega to the omega to the omega, 30 times or something. The worst case scenario is not so good. By the way, when I say that Gensen's proof by cut elimination doesn't have good bounds, that transformation on proofs has bounds f epsilon 0. So it in fact has to transcend that whole sequence. And so f epsilon 0 is sort of unimaginably bad. So in general, theorems could have really appallingly terrible bounds. I mean, the worst bounds in mathematics come out of people looking at these results and sort of cooking things up to actually achieve those bounds. But in practice, things are not so bad. So the reason proofs in P&O arithmetic can have terrible bounds is because in theory, a proof in P&O arithmetic could involve inductions over very complicated formulas, and almost no proofs do that. It's extremely unusual for people to even talk about statements with more than a few quantifiers, and they rarely do inductions on particularly complicated pieces of it. So as people have gone through actual proofs in the literature and looked at them, almost nothing gets you beyond basically like f omega plus n, so a little bit beyond the Ackermann function. And many actual examples are well below that. So in practice, it turns out even though ordinary proofs have all these tools available, most proofs just don't use them. These still are often not good bounds. We're talking towers of exponents or things like that, which proof theorists say, well, look how much worse it could have been, but no one else agrees with us about that.
Do any of them look at the question of what the sort of expected time would be on it?
As opposed to a worst case time?
Yeah, because you're talking about worst case
I
time.
am talking about worst case time. So these techniques aren't really suitable for analyzing sort of expected time. Kind of because there's no built-in notion of probability. And so any notion of expected time, you have to work in, well, what is your expectation? And so I don't know of any approach to that through this theory. So the idea here is, right, the proof theory isn't actually producing something new. What it's doing is taking a proof and telling you what bounds are there. So it can take a proof and it can tell you, well, actually hidden it looked like a proof by contradiction, but actually hidden within it, there was there were bounds, but the proof theory is not going to do hard math for you. It's not going to give you a new proof. So all it's telling you is what the bounds are. So in some sense, one way to read the proof theoretic results is saying, when it comes to pi2 statements, proofs and bounds are really intimately linked. And in particular, coming up with new bounds is really the same as coming up with a new proof. So in fact, what happens is these proof theoretic techniques can give you some bounds. Reasonably often, you're lucky enough that they're within the right order of magnitude as the real bounds. So it is not uncommon that the proof theory tells you the bounds are a tower of exponents, and when you actually get a proper lower bound, you discover it really is a tower of exponents. Hand optimization is always going to be these sort of automated techniques. This is a coarse technique. The proof theory may tell you it's a tower of bounds of size n squared, and then when you really work hard, you discover it's a tower of bounds of size n. That's something we really expect, that you're going to be able to do better if you hand optimize. And reasonably often, it turns out there's some other proof out there that actually is just a fundamentally different proof that has a fundamentally different order of growth. And so most of the examples I'm going to point out are proofs where there's a naive proof that uses Hilbert's basis theorem or something along those lines, and then there's a sophisticated proof using Grübner bases, and the Noetherianity is, Hilbert basis theorem is always going to give you Ackermannian bounds, and Grübner bases give you, at worst, about double exponential bounds. And that's just telling you the Grübner basis is really a deep new idea. It's telling you something fundamentally different. And none of these techniques are ever going to touch that sort of argument. So I want to talk a little bit about what these look like in practice. I haven't actually said what these extraction methods look like. And the examples, I'm never going to give, most of these simple examples have better proofs elsewhere, so I'm not attempting to give optimal bounds in any sense. I just want to kind of illustrate what these look like. So why, if pi2 statements are fundamentally constructive, why are there non-constructive proofs of them? So one reason is proofs by contradiction. I'll talk about those more later when I talk about ultraproducts. A second example is a lot of proofs of pi2 statements, of non-constructive proofs of pi2 statements, appear to be non-constructive because they have an intermediate step which is non-constructive. So one example is Noetherianity. So a lot of proofs in algebra go through the Hilbert basis theorem. And, right, so here's, I think, a correct statement of the Hilbert basis theorem. If you have an increasing sequence of ideals in a polynomial ring, then at some point this sequence stabilizes. And assuming that these ideals are computably presented in some fashion, either a computable sequence of generators or some other fashion, this is a pi3 end statement. It says for every sequence of ideals, there's some bound n, such that from then on, the sequence is stable. I'm cheating a little in two ways that I should point out, one of which is I'm now quantifying over sequences of ideals rather than over natural numbers. And so these for alls, as the exists, the bounds, but especially the for alls, are going to turn out to include more than just natural numbers. They'll include things like sequences and functions, and in general, they'll include anything that we could encode using natural numbers. And I'm going to use that sort of freely. I'm also assuming that testing ideal subsets is something we can do in a reasonable way. And actually, that's not completely obvious without, for example, Grübner bases or something like that. I'm just going to take that for granted for simplicity. So even assuming that, this is a pi3 statement, and it's really a pi3 statement. It's genuinely non-constructive. So we can cook up examples where you have a computable sequence of ideals, but if you knew where it stopped, you could compute the halting problem. So it's not. So this is what non-constructive statements should look like. So when you have a proof that depends on this, right? Typically what you do is the proof will use that bound n for where this sequence of ideals stabilizes. and it will use that to demonstrate that you have bounds for something. And once you've gone through that step, of course your proof is not constructive. That bound there really is a non-constructive number. So what the functional interpretation does is it tells us that when we have these non-constructive statements, there is a constructivization. Really, it's what we should call a constructive interpolant. There's some other statement that in general is weaker, but it's pi 2, and it captures all constructive content from the original statement. So in this case, the notion is local Noetherianity. So local Noetherianity is a little weird looking, and actually half the point of the talk is just to point out what this looks like, because it's going to be all over the paper with William. So we have a similar setup. You have a computable sequence of ideals, and we should have a function that tells us bounds on their degrees. And we have a new parameter, which is going to be a function from the natural numbers to the natural numbers. It's this function f. And what local Noetherianity says is there should be a bound n. It should be computable from the degrees d and from this function f. And it should give me this property. So it's local in the sense that it's not promising that the sequence stabilizes forever. It's promising that it stabilizes for a while. It stabilizes for a long enough time to do whatever we need it to do. And actually, in this case, this is, I think, equivalent to Noetherianity. Because if you were non-Noetherian, so of course, if you know a bound on Noetherianity, you just take it for your n, and of course it works. And on the other hand, if you're not Noetherian, then you have a function that gives you that tells you, well, for each n, here's how far I would go out to find a counterexample, and then this function would fail. But in general, that doesn't have to be true for these local versions. And the theorem that makes the functional interpretation work is, suppose you use Noetherianity to prove something that should have constructive bounds, to prove a pi 2 statement, then actually you can replace Noetherianity with local Noetherianity. The intuition here is that if your underlying statement is constructive, then how would you ever check that all the subsequent ideals are are actually contained? What is the rest of your proof of this pi 2 statement going to do? It's going to take the bound n, and it's going to do calculations and do whatever it's doing, and at some point it will look at some later point in the ideal, and some later ideal IM, and it will say, well, you promised me that IM was contained in IN. You promised me that this later ideal was contained in the ideal you gave me. And it might do this several times and look at several subsequent ideals, but it's fundamentally computable. It just can't go out and check all of them. And so this function f is just capturing, for this particular proof, how far out did you really use Noetherianity? You couldn't have used all of it. You only needed it up to some point, which might depend on n, but some function. And so this is basically how the functional interpretation works. It takes these complicated statements and it gives these local versions that are good enough if all we want to do is extract bounds. Yeah?
And in this theorem, f is really any function or any computable function?
F is, in this version, it can actually be any function. In general, it's a computable function. The pi 3 case is much simpler than the general case. So the pi 3 case, in the pi 3 case, the constructive version is equivalent and you can use any function. It's when you get to higher quantifiers that you start needing to be careful about the function should be computable. And the local version is strictly weaker, but captures the constructive content. Local Noetherianity, properly stated, is another of these pi 2n statements. And notice it now has a quantifier over functions from natural numbers to natural numbers. But for example, if these are computable functions, then they can be encoded by numbers. So we're not really sort of deviating from the general principles. So I wanted to give a quick example of what applying local Noetherianity looks like it's not the greatest example, but the examples that use local Noetherianity more robustly are also a lot more complicated. So this is a very simple application. So this is the algorithm for computing Grosvenor bases. And the details of the algorithm are not that important. The point is the algorithm very directly constructs a sequence of strictly increasing ideals right up until it stops. And it's not hard to calculate bounds on the degrees. You can go through, so there's a division algorithm application, and so you can go through the division algorithm and say, you add one new polynomial at each step, its degree is easy to calculate from the degrees of the polynomials you put into it originally. So if you know the degree of t0, you know the degrees of the polynomials you start with, you know the degree of each subsequent ideal, and one easy way to prove that it stops is just to apply the Hilbert basis theorem. And you just say, well, these are increasing ideals, so they stop eventually. And in this case, you can just take your function to be, you don't really care about Noetherianity. You don't care that the sequence stops forever. You care that it stops once. It happens to be a feature of the algorithm, then it's going to stop forever. But all you cared about was finding one step where it didn't get bigger. And that you can actually do constructively in, well, the function f of m equals m plus 1 and the bound on degrees, which is obviously where the bounds are really going to be held. So if you know the bounds on local Noetherianity, you can actually get a bound on the running time of the algorithm. It's not an optimal bound, so the bounds on local Noetherianity are Ackermannian. They're really Ackermannian. This is not a best known bound. This is provably optimal. I'll say more exactly about how it's provable later. So you know that essentially any use of of Hilbert's basis theorem that is not completely trivial is going to immediately give you Ackermannian bounds of some kind. The actual bounds are double exponential, but again, you need a better proof. Right? That's really telling you need real new ideas to get the better bounds.
I thought the Ackermann function has two parameters.
Oh, I hate that definition of the Ackermann function. Yeah, it's usually defined that way. So call this a of n comma n. So just plug in n for both of them for the moment. Because it's usually easier to think of bounds as being of one function. But you're right. The Ackermann function is usually defined as having two parameters. Okay. So I should say, so all I want to illustrate here is this illustration of why this local Noetherianity is typically good enough. There's some function. Here it's a very simple function. In general, it might not be. All right. So another not unrelated source of source of non-constructive proofs is ultraproducts. This is how William and I originally got into looking at this. So typically an ultraproduct proof that bounds exists goes by way of a contradiction. So it says, well, suppose the bounds didn't exist, then you could take a sequence of counterexamples and you could produce an ultraproduct. And in this ultraproduct, the statement should be false, but the statement is true in the ultraproduct, so it must have uniform bounds. And one way so the reason ultraproducts are useful for anything at all, like the reason anyone uses them, is what is called, at least in non-standard analysis, the transfer theorem. Right, so the transfer theorem is what tells you there's a relationship between what's going on in the ultraproduct and what's going on in the original structures you were looking at. And if you look at the transfer theorem, it actually exactly says that pi2 statements are the ones that should be related. So it's exactly concerning pi2 statements. This is in some sense where this definition got read off from, was looking at how the ultraproducts were working.
What exactly is for almost?
So it's almost all in the sense of the underlying ultrafilter. Yeah. So one way to state the transfer theorem is to say you have the sequence of structures and you have an ultrafilter that tells you for any set of natural numbers which half of it is this set almost all, or is its complement almost all. And the statement is that if one of these pi2 statements is true uniformly, right? So the witnesses have to work, the same set of witnesses have to work for almost every I. then the ultraproduct is going to satisfy this statement. And that's actually an if and only if. So what the functional interpretation is really telling us is what do you do in an ultraproduct? You pass up to an ultraproduct and you do whatever you were going to do. You work in it as a structure. And typically what happens is in the middle of your proof, you go through non-pi 2. You go through more complicated statements. And so one of the things the functional interpretation does is it tells us how to take complicated statements about an ultraproduct and translate them into statements about the original structures you were working with. Right, so this is a fact that I actually haven't seen people talk about much, that I think is interesting, which is an ultraproduct. There are two components that go into an ultraproduct. There's this sequence of structures, and there's an ultrafilter. And model theorists and set theorists have done a lot of work of talking about different kinds of ultrafilters and nicer ultrafilters and ultrafilters with extra properties. And outside of model theory and set theory, those don't get used. When people take an ultraproduct, they just take just any ultrafilter, which tells you that the ultrafilter isn't doing any work at all. It doesn't matter. All the information you care about must have been in the original sequence. And so the functional interpretation is telling you what happens when you have something that's true in the ultraproduct. What about the original sequence caused it to be true? So, I don't want to give this example that much. It's not that interesting. I'll give more examples in a minute. I should follow through on sorry, this is a little out of order. I want to follow through on a statement I made earlier that is relevant to the example I didn't just give. Which is I made this comment that Hilbert's basis theorem really always has Ackermannian lower bounds. And I should say that's actually because it's a theorem. So if you work in a weak theory that doesn't have the Ackermann function, so it typically can't prove that the Ackermann function is total, Hilbert's basis theorem is equivalent to the Ackermann function being total. So if you can use Hilbert's basis theorem, actually now you know how to make the Ackermann function work. So this is the sense in which really the Hilbert's basis theorem very strongly is going to have Ackermannian bounds almost any time.
What is RCA 0?
Oh, so RCA 0 stands for recursive comprehension axiom. Which isn't helpful at all. So it's a weak theory. It's a weak theory of second order arithmetic. So this came out of the reverse math program, where people were trying to come up with weak theories of arithmetic that were good enough to state lots of questions from mathematics. So P&O arithmetic, you can't directly talk about Hilbert's basis theorem because it involves sort of sets and you have to do a lot of encoding. RCA 0, you can talk about sets. So it's a weak theory of arithmetic, but it's built in a second order language. So you have natural numbers and you have sets. RCA 0 is sort of the standard weak theory to work over. So it says the only sets that you have are computable sets. The only sets you're promised to have are computable sets. And so and in particular, it's much weaker than P&O. So P&O arithmetic proves the totality of the Ackermann function. So it's not a suitable, it's not a suitable base theory. You can't prove this sort of equivalence in it because it already proves both of these theorems. So the nice thing about RCA 0 is it's strong enough to do all the encoding and all the sort of stating theorems that you want, but it proves very little that isn't very simple. For example, the only functions that it proves total are the primitive recursive functions. So it's a good base theory for proving this kind of equivalence. It's too weak to prove either of these theorems, but it can say in a meaningful way that given one, you can encode the other. And that's roughly what it's trying to do.
If you don't mind, could you remind me what totality means?
Oh, it's just the statement. So in for example, RCA 0, you can write down the definition of the Ackermann function. You can say, this is the function I want it to be. But RCA 0 can't prove that for every n, there is an m that is equal to the Ackermann function of, say, n comma m.
Okay.
So totality is the statement. So you can write down a relation that would be true. You can say, you can check if, say, the Ackermann function of a comma b is equal to c. But RCA0 can't prove for every A and B there exists such a C.
Or the other way?
Hmm?
For every C there is an A and B?
No.
No.
It's so
Not surjectivity, but totality, meaning the domain of the function is the whole
Yeah.
natural numbers.
Defined everywhere.
Defined.
Oh, the domain.
Yeah.
Oh,
Yeah,
okay.
exactly. Yeah, it can't prove that it's defined everywhere. You can say how it should be defined, but it can't prove it's defined everywhere. Okay, so this is the theorem about, or the version of this stuff about the functional interpretation stated for ultraproducts. And what it says is, if you have a sequence of structures, the KIs, and you have their ultraproduct K star, and you look at some statement in first order logic about the ultraproduct. So you look at the statement sigma star, and here's sigma, it's a statement of first order logic also with quantifiers over, let's say, the natural numbers. So it's in the class of these things like these pi to n statements. You have both quantifiers over K star, maybe K star is an ultraproduct of fields, so you have quantifiers over the field, but you also have things like quantifiers over the degrees, over degrees of polynomials or things like that. Then actually there's a related statement which is pi 2, and this statement has to be uniformly true in the original sequence of structures. And Alice is making faces at me, yeah.
Are you assuming, I mean, if this theorem really is for one fixed sequence of structures and one fixed ultraproduct and one fixed sigma, then it has kind of no content, right?
So I'm saying that you can extract the relationship between sigma and this statement sigma nd doesn't depend on the particular structures you're talking about. Yeah, there's a general translation for statements independent of just about everything else.
So what you're saying is that for somewhere at the beginning of the theorem, for every
Yeah.
sentence sigma, there is a sentence sigma nd, such that everything else holds.
Yes. All right. And the way I want to interpret this is exactly the way I was suggesting earlier, that this really tells you how to look at an ultraproduct and say, I know what's true in the ultraproduct, what was true of my original sequences to make it true. So I'll come back. Oh,
So that's the kind of the converse of the previous theorem?
um,
Can you back up?
Can you back up for a moment?
yeah.
So the theorem was that, what? You have a sequence of this thing satisfy that, then the ultraproduct would satisfy that, right?
Yeah.
So is it the
So,
other way?
well,
Or are they related, the two theorems?
well, I'd say they're useful together. So the previous theorem said if you have a pi 2 statement, that statement by itself, it's uniformly true in your sequence exactly when it's true in the ultraproduct. And this is saying, well, and so the question is, what do you do with statements that aren't pi 2? And what this is really saying is, here's how you can take any statement and turn it into a pi 2 statement. So that in the ultraproduct,
Any statement.
this pi 2 statement is equivalent to the original statement. But because it's now pi 2, its truth in the ultraproduct is related in an easy way to its truth in the original structures. And so the point is they work together.
So what's the corollary? What's the corollary then, when you put them two together?
So when you put them together, this exactly says if you take a statement in an ultraproduct, then there is a translation that gives you a statement so that the truth of sigma in the ultraproduct is equivalent to uniform truth of this statement in the sequence
So
of
that's why I
structures.
thought it was the converse, the other statement.
Yeah.
Okay. All right.
So the fact that the extra quantifiers that you're getting are all the natural numbers has something to do with the fact that your ultraproduct is indexed by natural numbers?
No.
That your filter is on natural numbers, no?
No. So actually, this would really be true if you were indexed by more complicated things. Yeah, I mean, the fact that the extra quantifiers are over natural numbers. Let's see. What do I want to say? So really the point is I want to talk about statements that consist of first order logic plus quantifiers over the natural numbers. And I want to focus on those really because if you look through the literature and how people use ultraproducts, that's what people use ultraproducts for. You can adapt this to things with quantifiers over more complicated domains. But no one has really written down the general theorem for exactly what you can do that over because it just gets messy. And this covers almost all examples.
So the upper script ND stands for?
Oh, good question. So D is Gödel's dialectica interpretation, which is called the dialectic interpretation because that's the journal he published it in, which is not how we name things, but that's how it's named anyway. This is why I'm really pushing for functional interpretation, which is, I think, a better name. But the N is what's called the double negation translation, which is a translation of classical logic into constructive logic. And so Gödel's dialectica interpretation is actually a translation of constructive logic into constructive logic in higher types. And then when you put them together, you get from classical logic to constructive logic in higher types. And it's this combination that's useful for us, but it's originally written as this factor transformation.
So the sigma ND, is it computable from the sigma or not?
Yes, it's computable. I want to say easily, though you'll disagree with me after I show you some examples. But it's certainly computable. It's linear time computable.
Oh, okay.
Yeah.
So the reason I was asking my previous question is that my gut instinct for how these how the uniformity of bounds works with ultraproducts is that if your bound is not uniform, then you build a countable sequence indexed by the integers and use the indices in the sequence to diagonalize against your bound. So you're saying that that's not salient to this theorem.
Well, so assuming you're talking about, I mean, you just need a countable sequence.
Sure. But what I'm saying is that what about uncountable sequences?
So if your ultraproduct is countably, if your ultraproduct is countably complete, if your ultrafilter is countably complete, totally different things are going to happen.
Right. Okay.
Yeah.
Okay. That was my question.
Yeah.
Okay. Well, that's a much better formulation of my question.
All right, so I want to give some examples. I think I stated this theorem, first of all, not very precisely, and secondly, it's a technical theorem, even when stated imprecisely. So I want to give some I think some examples will make this a bit clearer. So, in fact, when I originally was looking for examples in the realm of sort of field theory and differential field theory, and I sort of went through Hans's book and combed through every statement, and actually, a lot of it turns out in this area, there's not as much use of higher quantifier statements, even once you're in the ultraproduct, as I'd expected and as there is in other areas. So I want to quickly go through some of the examples we've seen in other areas that will at least illustrate what this translation looks like. So the best studied example, which is sort of the example that motivated a lot of this, came out of this correspondence between additive combinatorics and ergodic theory. And fortunately, we don't need ergodic theory. We just need to talk about convergence of sequences, right? So, if you take the classic statement that a sequence, Calc 1 statement that a sequence converges, for every epsilon, there's an n for all m, and you do this translation on it, you get what's called metastable convergence, or locally stable convergence. And it looks a lot like that local Noetherianity statement. So you say that for every epsilon and for every function, you have an n, and the sequence is stable, not as ordinary convergence would have it forever, but stable between n and f of n. Right? So it's stable for a while. And this turned out to be useful because it lets you translate between stuff going on in these ultraproducts where you can do sort of real ergodic theory and analysis, and stuff going on in finite structures where you have other tools and where you can be a little sloppy about certain things. Yeah.
Well, that's a stupid side question. Is there an obvious example of a sequence, say, of the reals that converges metastably but doesn't converge?
No, because it's the underlying statement's pi 3, so metastable convergence and conventional convergence are equivalent. If you want